Good morning, mathematicians. Got another live stream broadcast. Um, yeah, I guess we'll start off by looking at. There's a comment from my channel that I wanted to just address out loud because I didn't want to do that much typing. Yeah, I guess it was this question here on my video about the axiom of choice. So, yeah, basically their question is they were wondering about what are some disadvantages in your line of research about a lack of basis. Yes, that's a good question. But I wanted to sort of oh, you know what I'm going to do before I answer that? I saw someone once did some set theory videos, and they had like they called it like a boredom avoider or something. Because I guess no one has any attention span these days because we all watch too many TikToks. But their upper top corner was the Mandelbrot set Zoom. So I think what I'm going to do is, well, hopefully it's not
From
like
idea to submission.
copyright or something. I'm going to put on the Mandelbrot Zoom, so that way when I'm just talking about random stuff, people aren't bored. Yeah, there we go. Mandelbrot Zoom. Okay, so what was I trying to say here? Yeah, so their comment was about when a basis is useful, or rather when not having a basis is a problem in my line of research. The thing is, I don't necessarily know a lot of explicit examples that immediately come to mind. Part of the thing is that, well, if you have on the part of my research that deals with the representation theory of p-adic groups, there's infinite dimensional representations. So there's some like functional analysis going on in the background. So it's definitely possible that somewhere there's some assumption of a vector space. There's some need to have a vector space have a basis, and that you need the axiom of choice to get away with that, basically. Oh yeah, someone in chat asked, "What's the menu today?" Yeah, not sure. Don't have a plan. I'm just talking about a comment from a previous from my axiom of choice video, and then probably I don't know. We'll like look at Reddit for some math news, or maybe look at Archive or something. Look at interesting paper names together, or maybe there'll be questions in chat. Anyways, the other place I guess we're not having a basis maybe affects my own personal research is in when it comes to modules in general, because there's maybe I should just get out the writing pad and like draw some stuff down while I'm talking. So we have so if I have some ring and I have some modules. Okay, so I apologize if there's people who aren't familiar with these concepts in the stream, but one of the things I study is representation theory. So if we just think about a finite group for a second, and a representation of that group, so that's equivalent to giving a homomorphism to the invertible maps on some vector space. It turns out that one tool for studying this is that you can instead build a ring called CG. So this is just complex valued functions defined on the group. It's just the ring of complex valued functions on the group. And you can give this a multiplication and addition structure. So this basically has the structure of a ring. And now you can turn, you basically have a process that turns representations of your group into modules over this ring. And in fact, the sort of fancy way to say this is you get an equivalence of categories. And basically that just means essentially that, studying representations of a group is everything you could possibly want to know you can do in terms of modules. So that makes life easier in a certain sense. But module theory, generally speaking, is also can be difficult. So I do a similar thing sometimes with something called a p-adic group. We won't worry about what that is. An example, if you happen to know what the p-adic numbers are, is GLQP. And we have to come up just simply taking the collection of complex valued functions on this group is no longer going to do, because there's topological considerations to worry about. And so there's some other ring that we have to come up with and study. But mind you, as I'm saying this now, this ring, you can give it a vector space basis, but I guess it doesn't necessarily have a module basis. And so that can maybe make things trickier. Yeah. So I don't know if that answers this person's question. But let's look at some other. Yeah. A lot of comments on that recent video. That's good. Yeah. Okay. Let's maybe see what does Reddit have in store for us on Reddit Math today. Interesting. Okay, maybe we'll check out this one. Currently, senior year of high school, extremely passionate about math research, specifically number theory. My dream is to pursue a Ph.D. in this area. However, there's a problem. Well, okay, definitely not a deal breaker. Just because you perform below expectations in math contests. Math contests, as I think a number of people know these days. Oh, someone asked, about the official name for the CG. So it's called the group ring, or the group algebra of G. So that's the term you could look up if you want to read up more about it. So yeah, this person's asking. Yeah. So lots of people, as they'll tell you, math competitions are like running a sprint race, whereas research is more like a marathon, right? And do you perform well when practicing the contest? Yeah. Unable to make the required observations under pressure? Yeah. So there's no need to make those observations under pressure. Unless maybe you're become a quant trader after your mathematics degree doing math finance or something. But most times, or I don't know, maybe there's military things where you make snap decisions, but even then you're probably just designing stuff. So mathematicians writing proofs, you're never really doing stuff under pressure. It's a long game. But enjoy doing research. Yeah, so I mean that spend 8 to 10 hours every day on a problem that interests me. That sounds like a mathematician in my mind. Euler already reached that stage before me. Yeah, that's going to happen to you a lot. I think that happens to every mathematician. You, at some point in your life, it's maybe a rite of passage. You think you discover your own thing, and then Euler did it already. So yeah, definitely this person should pursue math if they want to pursue math, 100%. Okay, a couple more questions in chat. Yesterday, explained a bit more about modules. What are they? Why do we need them? Yeah, okay, sweet. So I'll talk about that in a second, but there's one other question that's a little bit easier to answer first. Did it take a break in between undergrad and grad school? No. However, when I first started going to university, I dropped out not long afterwards, and I just basically spent a couple years partying because that's all I was interested in at the time. I mean, I still loved math even back then, but I dropped out to spend a few years doing that, and then eventually that got kind of old, and so and then it was like many years, like a number of years later, that I went back and started like seriously pursuing my degree. So I kind of had a break then, and then after that I returned to my undergrad full time, and since then it was undergrad, master's, Ph.D. without any break. Okay, let's jump into an explanation of modules. So we did talk a little bit last time about so here's like a first definition of modules. Or a first example, I should say, of modules, right? So last time we said we were looking at the plane R2, and we said, oh, like R2 has got, it has some, yeah, that's obviously a thing that we like to study, the real plane. But then also, you could imagine this infinite grid of points, and you could very well ask yourself, well, what if we just thought about those collections of pairs of points that were integers? I mean, there's some sort of geometric interpretation of this, but there's also just algebraically, right? Like sometimes, like, integers are particularly nice, right? Like real numbers can be all of these crazy, weird irrationals. So it might be nice to ask if we have this sort of simpler algebraic structure sitting inside there. So that's the first thing, right? That this may be like a first example where you look at the so I mean, this isn't really motivation for why you should care about modules. We'll get to that in a second, but for example, you might just be curious. I pulled up last time the vector space axioms, and you might just be curious. Well, do you really need a field in the vector space axioms? And we sort of looked at it last time, and we saw no, it's really just about having multiplication and addition. And so it's just very natural to ask, well, is there really a larger structure going on here, right? It's a useful thing to sort of like get rid of the unnecessary details and assumptions and see how far you can push things. So someone mentions the definition of modules as ring actions. Yeah, definitely, that's a good definition, and we'll get to that in a second. I mean, really, we haven't properly defined them yet. So, I think last time I said, let's pull up the vector space axioms again. So, yeah, you literally, one way to define them is you literally just look at these statements here about what defines a vector space. And so all of these other things you keep the same, the things in your modules, it's basically the slick way of saying this. It's an abelian group under addition. And then really the only thing that changes are these these conditions that involve a scalar multiplication. But now instead, usually the vector space axiom We assume that the scalar field here, it says real numbers, but we generally consider it to be, an arbitrary field. All you do to get to modules instead is you now just imagine it's a ring. And generally we want a ring with an identity element, but not always. In fact, that even comes up in some of my work. So what's another? So why might we care about them? I don't know if you were here when I was talking about this in the stream, but I was talking about there's this process in representation theory where one wants to study the representations of a group, and in fact, it turns out that studying the representations of your group is actually equivalent to studying modules over the ring of functions on that group, complex valued functions. So if this is a complex vector space. So what's the point of that? Well, it's just to say that we do have this theory of modules out there, and if we do develop this theory in generality, then anytime modules arise in mathematics, we can apply those general things that we've learned about modules and use those facts in the study of whatever object. So one example is this case, like for finite groups, we can turn representations into modules. Now, representation theory of finite groups is pretty understandable just at the level of representations, and I like thinking about things at the level of representations there. So you could argue that there is maybe not a huge advantage to switching to the module perspective here, but one thing where it gets really useful is in my research, there's cases, so I'm studying groups that look like this. So whatever the p-adic numbers are, there's lots of great explainer videos out there. But so GLN QP, this is just n by n matrices. But instead of like putting in the real numbers or the complex numbers to each of those components, invertible matrices, you put in the p-adic numbers instead. And it turns out, this big group, for finite groups, all your representations are finite dimensional. For this big group, you could possibly have infinite dimensional representations. So that's inherently infinity's trickier to deal with than finite stuff. So that's going to make things a little more complicated. But there's a sort of special subset of the representations. I'm not going to say what that subset is now. I'm not going to explain it, but there's a special subset of these representations where you can find a special kind of ring called the Iwahori-Hecke algebra, or affine Hecke algebra. Comes up a bunch of places in mathematics. But it turns out that if you take one of these representations and you plug it in over here, you take the corresponding module over that ring, it becomes finite. They all become finite dimensional. And so that is great. It's so much easier to sort of like get a grip on it and really sort of explicitly see the structure. So that's one advantage. So as mentioned in chat, modules are vector spaces with the field replaced by ring instead. That's totally correct. And a ring is basically a field without division. Yes, that's definitely correct. One other thing too, though, that a ring that we often drop for a ring, so fields we normally demand they're commutative, which means like multiplication is commutative. For rings we don't. And so a very practical example is the ring of 2x2 matrices, right? So this is a ring, like we can add matrices together and we can multiply matrices, but as you probably know, in general, matrix multiplication is not commutative, so A times B is not going to be B times A. And by the way, there are things called division rings, which do have multiplicative inverses, but do not have commutativity. My favorite example of this is the so-called quaternions. So this is just the set of all A plus BI plus CJ plus DK, where A, B, C, and D are all real numbers. Oh, this has jumped up. I actually assigned my Algebra 1 students in their tutorial, I gave them a bonus problem about the quaternions. There's this really cool fact about the quaternions I like. So number one, this is a division ring. So for all quaternions, there exists, all non-zero quaternions, there exists an inverse, such that if you multiply them, you get to 1. Left and right inverse simultaneously. And here, because multiplication's non-commutative, it's good to specify both of those things. And here's one of my favorite facts. I learned this in a course about modules and polynomials over non-commutative rings. So there's this cool theorem. So it turns out if you look at polynomials whose coefficients are valued in the quaternions, it's possible for a polynomial of finite degree to have infinitely many roots, which is wild, right? If you take this cubic polynomial, that this polynomial should have at most 3 roots in the real numbers or complex numbers, but over non-commutative rings, it can have infinitely many roots. However, there is a generalization that actually implies the classic theorem, for commutative rings, that a polynomial has at most n roots, and it's that for all polynomials in here, P of x has at most degree P of x conjugacy classes. Of roots. So what I mean is, this polynomial, if you find a root, right, there could be infinitely many distinct elements of the quaternions that make this polynomial equal to 0. However, you can find finitely many, in fact, at most, so m, where m is at most the degree of the polynomial, finitely many quaternions, such that if some quaternion makes your polynomial equal to 0, then there exists some other quaternion such that if you conjugate, so that means multiply on the left by the element, multiply by the right by its inverse, it will be equal to one of these finitely many things. So that's crazy. I love it. Okay, we got a lot of stuff going on in the chat for me to catch up on here. Explain the motivation for the definitions of irreducible and prime element in an integral domain. Yeah. Let me just catch up on the other questions first and see what's going on. So closure is what holds all theory. All those commutative algebra books, yeah, start with all rings are assumed commutative. Yeah, I mean, commutative rings are amazing, but I'm forced to study them in my own research. Quaternions is division algebras. Algebra can also be a ring. Yes, algebra is are special cases of rings. They're very nice kinds of rings. I don't know if Gauss hated the quaternions. I don't know if the quaternions even existed in Gauss's time yet. I don't think we knew about them yet. Yeah, exactly. Conjugacy classes give us a generalization of the fundamental theorem of algebra. Oh yeah, so okay, I am gonna go back to this prime element stuff in a second. Yeah, sorry if I confused anyone with jargon. But well, the that's the thing with having a sort of online office hour is, there's probably people in here who are like still in high school, and there's maybe other people that are like have more advanced, deeper knowledge than me. Certainly based on my comments, there's people watching from all levels of knowledge. So it's very hard to give an answer that's satisfying for everyone. But I guess I probably should have geared it. You did mention you're in physics, so I probably should have geared it more to a physicist palette. But I got a little carried away. Anyway, I want to address this question from Antoine, though, about what it means to evaluate a non-commutative polynomial. That's a very, very good question because, for example, like, if you have this polynomial, this is p of x, what does it mean if things are potentially non-commutative? Like, that, if you evaluated it by just plugging in r here, compared to, well, I've chosen real scalars, so in the quaternion it won't make a difference, but let me call it 3i. Let me put 3i there, right? That in general will give you a different answer than if you had organized your coefficients on the other side. So actually there's, I believe in the course that I took, we took the convention that we always arrange all coefficients to go on the left side of the polynomial. Of course you can write that the whole theory is just like basically the same if you write things on the right. Well, structurally the theory is the same, of course. Literally, right, the two conventions will lead to different answers for specific polynomials. And then I think there is also another convention where you don't let the variable commute at all, and then you have both left and right coefficients, and you just need to be very careful when you're multiplying polynomials of how you keep track of those. But yeah, normally for the statements that I said above, where I know it's true, is that you just, after you do your multiplication, you just always move the coefficients to the right. So then, yeah, I guess it's not necessarily consistent with doing like evaluating px qx, multiplying that first and then evaluating. Yeah, I'm a little hazy on this now, actually. But I do remember in the course we had some convention of moving everything to the right. I think one of the texts was YT Lam. I think that was one of the texts that we were using. Okay, so let me scroll back up here. So I don't know if this is too intuitive, but can you please motivate the definitions of irreducible and prime element in an integral domain or wherever they make sense? Yeah, so definitely prime element. So, well, one example here is that, so of course we have like the integers, right? This is sort of the one ring to rule them all. And in the integers, we know that we have prime factorization, right? So every integer can be factored into plus or minus some product of primes where it's unique up to rearrangement of the primes, right? And then this is nice because you can sort of, you can prove things using this prime decomposition business. So then naturally, though, I mean, the integers are a ring, and so naturally you might wonder what are other rings in which we can define a notion of primeness, right? We want a notion of divisibility, we want a mention of primeness. So if we take the Gaussian integers, I see a good question in chat about tensor products. We'll get there in a minute. So these are the Gaussian integers, and one way to write these. So this is just all a plus bi. So it's basically it's complex numbers with integer coefficients, basically. And it turns out that in the Gaussian integers, things that used to be prime in here are no longer prime. So what I mean by that is, for example, 2 now becomes the product of 1 plus I, 1 minus I. 3 stays the same. 5 becomes a product of 2 plus I, 2 minus I, and so on. There's an interesting number theoretic description of this. Okay, but now what do we mean by prime in this other case? Right? Like, again, we have there's divisibility and 1 by itself and whatnot. So how do we come up with a new definition of prime? Well, one of the hints as to what the right definition should be is to look at the old definition of prime, and it turns out an equivalent definition is that P is prime if and only if for all AB in the integers, if P divides AB, then P divides A or P divides B, right? So this is our new way of so here there's hope that this can be generalized, right? So this we could replace with ring. And then the only other thing we would need to do to generalize being prime is to, Gaussian integers are a ring, so the only thing we need to do to generalize this definition is to say what it means to be divisible. So, but again, that's pretty easy, right? In the integers, m divides n, if and only if there exists a k in the integers such that n is equal to mk, right? And now again, it's easy to see how we generalize this because all we need to do is replace this with an arbitrary ring, and here we're only using ring properties, right? This would just be ring multiplication. So that's why we would and then one would hope, just like having prime factorizations is a useful tool for proving things in the integers, having prime factorizations in other rings could also be a useful tool to say, okay, well, I have this sort of, I can take every element, instead of having some weird arbitrary element, I know I can factor it into this standard form that has this prime factorization. Okay, not all rings have a nice prime factorization. There's unique factorization domains are the sort of ideal world for this. And then also, the same thing with the notion of irreducible, right? So, like if I'm in Rx, right, the polynomial x squared plus 1 is irreducible. And what this means is that I can't find, so there does not exist polynomials, say P and Q, such that P and Q are not equal to the original polynomial, but their product is, right? We need to modify this slightly. So we say not the original polynomial or not the identity. We also need to generalize the notion of units a little in order to talk about this more generally, which just deals with multiplicative inverses in the ring. So, is it fair to say rings are generalizations of integers and fields are generalizations of real numbers? I think so. Yeah, that wouldn't be a terrible way to think about it. Rather, yeah, because I think historically, like, those are, like, the integers was one of the first rings we really studied, and the real numbers, like, those are sort of most concrete real-world examples of these things. And, yeah, so definitely that's what we had a grip on first. And then later went on to study other things. So that's a bit about that. I think I'm going to wrap it up soon for today. But let me see. So we have this question. Reading a Luffy, he mentioned tensor products satisfy coproducts in the category of commutative rings. I don't understand why tensor product would not just satisfy products. Good question. I see Antoine here answers the categorical product in the category of rings is just the usual product, not the tensor product. Yeah, exactly. So I think it just comes down to, like, writing down the universal property, right? So in fact, I was doing this. I have a student I'm mentoring. I started a mentorship program at my university, and I'm also participating in it. We were talking about products the other day, and so I recommend going through the example. Try and prove that the set theoretic that the Cartesian product of sets satisfies the definition of the categorical categorical definition of a product in a category. So yeah, because I'm gonna go soon, I'm gonna sketch why this is true for you. So I'd say one is do this for sets. Go through the exercise of sets. Convince yourself that the Cartesian product of two sets satisfies the universal property for sets, right? So actually, I should say a product is not just an object. This is a product is not just an object. It is technically a triple, right? It's an object together with your specified projection maps, right? So show that the Cartesian product together with the maps that, of course, just project on the first and second factors, show that this satisfies the universal property of products for sets. That would be number one. And then number two, I would say, is try and then do the same thing for rings, right? So take two rings, think about the Cartesian product. How would you define a ring structure on this object? And then consider the same thing. Consider the two projection maps, and RS, I'm going to call it T. And again, show that this thing satisfies the universal property in the category of rings. And now all you would need to do to see why this doesn't give you the tensor product is just to try and find an example where the tensor product of rings, so I'm assuming we're taking the tensor product over the integers, is not isomorphic to the ordinary product, right? So somehow this is, in general, it'll be like smaller than the original product, right? Because normally in the product, you can't really like move things across between these two elements, but as soon as you can move things across here, then yeah. Anyways, sorry, I see there's a bunch of other stuff in the chat, but I think I'm going to call it for today. So thanks everyone for joining me. Probably gonna be doing plenty more office hours in the near future. So I'll see y'all then, and yeah.